Hello everyone, my name is Sara Sandh, and this summer I worked on an HPC project at Spectral in Paris. My project is about improving an existing software that simulates seismic wave propagation by implementing a better stability condition for the numerical methods. At this point, it might sound a little unclear, but don't worry, I will take everything one step at a time. Before we get started, I will talk about what seismic wave propagation is and why it matters. After that, I will move on to how seismic waves are simulated. Once that is clear, we can start discussing the problem with stability, and this will finally lead us to my job, which is how to implement an eigenvalue-based stability condition in an HPC environment. So first of all, what are seismic waves? They're waves that travel in the Earth or on its surface. This can come from a lot of different things, such as earthquakes, volcano eruptions, or even man-made explosions. The reason we care about how these waves propagate is simply because if we understand how they propagate, we can understand how it affects, for example, the buildings and infrastructures around it, and then even minimize or prevent the inflicted damage. This is probably pretty clear, but why do we actually need the simulations? Well, we're looking at a wave propagation problem that is very big and complicated. We have incredibly large domains, weird geometries, and largely varying material properties. This makes it very difficult to just solve a simple equation and be done with it. It's also not really a problem that we can set up ourselves easily. We can't really sit around and wait for the next earthquake to occur, and we definitely don't want to try to reproduce an earthquake just to see what happens. Now that we know why we want to simulate seismic waves, we can move on to how. This will unfortunately be a very shallow explanation, but I've written a blog post that goes into more detail if you want to know more. What we want is to solve the wave equation, which is a second-order PDE in space and time. This can be done in 3 steps. Step 1 is to split the variables. Earth is 3-dimensional, and of course time adds an extra dimension. This means that we have a 4-dimensional problem, which is a little bit complicated. For this reason, we will separate space and time, and this is called semi-discretization. The second step is to formulate the 3-dimensional spatial problem. For this, we use something called spectral element method, which is a type of finite element method that actually makes our mass matrix M fully diagonal. This formulation gives us a second-order ODE in function of time, which can be solved with a much easier scheme. This takes us to step 3, to solve the system in time. For this, we will use a time-stepping scheme, which is just what it sounds like. We start from time 0, move forward one step at a time, and use the previous step to calculate the next one. Because we only need to calculate m and k once, the majority of our simulation time typically goes to this time-stepping. The smaller time step we use, the more times we need to repeat the calculations. Unfortunately, there's a limit to how big our time step can be without losing stability. Because we don't want to do unnecessary calculations, we want to pick a time step that is just below the stability limit. This might sound easy enough, but unfortunately it isn't. The stability condition we often talk about is the CFL condition, in which the largest allowed time step is determined by the element size. This is very easy to calculate, but unfortunately it doesn't work with heterogeneous media such as the Earth. What is currently used in the wave propagation software is an additional safety factor. To ensure stability, the calculated time step is then multiplied by this safety factor. The problem with this is that the time step will be very, very small, so we're performing a lot of unnecessary calculations. The better option is to implement a more advanced stability condition, and this is actually my job. In fact, the maximum allowed time step can be bound by the largest eigenvalue of the mass and stiffness matrices computed in the spectral element method. There exist a lot of different libraries to solve the eigenvalue problem. Unfortunately, most of them are not appropriate for HPC applications. So, what is the problem with the existing libraries? Well, most eigenvalue solvers need the full matrix. In HPC applications, however, we're often working with very large and sparse matrices. This means that almost all our elements are zeros that we don't actually store. If we would have to assemble and store the whole matrix just to calculate an eigenvalue, it would require a lot of memory and massively reduced performance. Luckily, we're not the only ones with this problem. In fact, this is the reason that the RPAC library was developed. This library uses a so-called reverse communication interface, which means that instead of passing the whole matrix to the solver, the user only needs to write a function that computes the matrix vector product. This means that the solver doesn't care how or even if the matrix is stored at all. So now to the big question, did it work? Of course, solving an eigenvalue problem takes longer than applying a safety factor to the CFL condition, but actually for the test cases I ran, the calculation of the new time step was significantly smaller than the rest of the simulation. In fact, the new time step calculated with the eigenvalue would typically be twice as large as the time step with the safety factor. Because the eigenvalue solver is so fast in comparison, it means that for most of the test cases, the overall computation times were actually cut by at least half. So that's it for me. Thank you for listening, and don't hesitate to reach out to me if you have further questions about the project.